So here's the question this whole video comes down to. If a network token is basically a stored credential, why would you even need an orchestration layer to use one? And let me give you the short answer up front. A network token isn't a credential you save once and replay. Every single transaction needs its own, fresh, single-use cryptogram. One payment touches the card network's token services, an acquirer like Stripe or Adyen, and a PCI-scoped vault. And it can get declined in ways that a retry would actually fix. That per transaction work is the whole job, and an orchestration layer exists to own it. Because the benefits were never really the question. Lower PCI burden, tokens that quietly update themselves when a card is reissued, lower transaction cost, and usually a few points of authorization rate lift. All of that is settled. The real question is, who does the work on every transaction that lets you actually keep that lift? So think of the orchestration layer as owning three things your app would otherwise have to own itself. First, multi-party choreography. A single payment touches the card network's token services, one or more acquirers, and a PCI-scoped vault. And each one of those is a separate system with its own API and its own ways of failing. Second, per transaction state. A network token isn't a credential you fetch once and reuse forever. Every authorization needs its own fresh, single-use cryptogram. So the orchestrator generates a new one for each transaction and drives it all the way to done. And third, failure recovery as policy. Tokenized transactions sometimes fail in ways a retry would fix. Knowing when a tokenization call has failed, when to fall back from the network token to the card number, and when to just stop. That's intelligence the orchestrator carries, so your app doesn't have to. So for the rest of this video, let's actually watch the orchestrator do that work, one flow at a time. The first time a customer pays, that first payment is a cardholder-initiated transaction, or CIT. The merchant app sends one call and waits for one response, and if you walk through the diagram, you can see everything the orchestrator does in between. In step 1, the app sends post payments confirm with the raw card in the body. Now watch the two calls to the token service, because they are two calls, not one. In step 2, the orchestrator provisions the token. It asks the network's token service, Visa Token Service or Mastercard MDES, to issue a network token for this card. For step 3, the token service returns the token and its status. In step 4, there's a separate request that gets a cryptogram. Step 5 is where the token service returns it. Provisioning the token and generating the cryptogram are distinct operations, so keep them separate. In step 6, the orchestrator sends the authorization request to the acquirer, like Stripe or Adyen, carrying the token and the cryptogram. For steps 7 and 8, the acquirer forwards to the issuer and the issuer approves. Step 9, the approval comes back to the orchestrator. Step 10, the orchestrator returns payment success to the app, along with a payment method ID the app stores for next time. If you count the internal hops, there are 8 messages between the orchestrator, the token service, the acquirer, and the issuer. From where the app sits, they only see one request and one response. Now let's take that same customer's second payment. They're back, checking out with the card they've already used, and this is still a cardholder-initiated transaction, a CIT, because the customer is right there tapping pay. So watch how much shorter this diagram is than the last one. In step 1, the app sends post payments confirm, but this time with a saved payment method ID instead of the raw card. And here's the big difference. There's no provisioning step. The network token already exists from that first payment, so we skip straight past it. But look at what didn't disappear. Step 2. The orchestrator asks the token service to get a cryptogram for the token. Step 3. A fresh cryptogram comes back. And that word fresh is the whole point. Cryptograms are single use, so even with a saved token, you can't reuse the old one. Every payment gets a brand new cryptogram. Quietly, this is also where the orchestrator reads the card network to know who to ask, Visa Token Service or Mastercard MDES. From there, it's the path we already know. Step 4. The orchestrator sends the authorization request to the acquirer with the token and that fresh cryptogram. Steps 5 and 6. The acquirer forwards to the issuer and the issuer approves. Step 7. The approval comes back to the orchestrator. And step 8. The app gets payment success. So here's the takeaway. A saved token saves you the provisioning round trip. It never saves you the cryptogram. That per transaction cryptogram is the part that never goes away. A merchant initiated transaction, or MIT, does not involve the cardholder at all. For example, when a subscription renews or an installment comes due. From there, the charge fires on a schedule. Let's walk this diagram against the last one and see the differences. In step 1, the app sends a scheduled charge with the stored payment method ID. There is no provisioning here. The token already exists from the original payment, so the flow goes straight to the cryptogram. So step 2, the orchestrator goes straight to the token service and asks for an MIT cryptogram. Step 3, the token service returns a cryptogram marked merchant initiated. That marking matters because a cardholder present cryptogram and a merchant initiated one are not interchangeable, and the issuer treats them differently. Step 4 is the step that carries the most. The authorization request goes to the acquirer with the token, the MIT flags, and the original transaction reference. The flags mark the kind of merchant-initiated charge: recurring, installment, unscheduled, or no-show. The original transaction reference points back to the cardholder-initiated payment that first set up the mandate. In Hyperswitch, that reference travels as the network transaction ID carried alongside the token. Steps 5 through 8 run the same authorize and approve path back to the app. So, why does all that stamping matter so much? Well, here's what happens when you get it wrong. Miss the flags or miss that reference, and the issuer looks at the charge and sees what looks like a normal cardholder purchase. Except there's no cardholder anywhere in sight, and that mismatch is an easy decline. So, nailing this on every single scheduled charge, that right there is how orchestration works. Alright, here's the last flow, and I think it's the one that really shows why this layer is worth it. It opens as a plain repeat payment, a returning customer paying with a card they've used before. So let me set the scene. Step 1. The app sends post payments confirm with a saved payment method ID. And notice, the cryptogram step hasn't gone anywhere. That's steps 2 and 3. We ask for a cryptogram for the token, and it comes back. Remember, cryptograms are single use, so having a saved token doesn't get you out of that call. Step 4. We authorize with the token and the cryptogram. Steps 5 and 6, the acquirer passes it to the issuer, and this time, the issuer says no. Declined. Now, why even fight a decline? Good question. Here's the part a lot of people don't realize. Issuer fraud systems don't always score a tokenized transaction as well as they'd score the raw card number. A lot of those models were trained on card number data, so they've simply seen fewer tokens. Which means, and this is the frustrating bit, a payment can get declined as a token when that same payment would have sailed through as a card number. So watch how the orchestrator fights back, steps 7 through 14. Step 7. The decline lands back at the orchestrator, and the first thing it does is ask a question. Is this decline retriable or not? And this one is. It's that network token to PAN case. So step 8, it fires off a detokenized request to the token service. Step 9, the clear card number comes back. Step 10, it retries the authorization, except now it swaps the token out and sends the card number instead. Steps 11 and 12, the issuer takes another look, and this time it approves. In steps 13 and 14, that approval makes its way home and the app gets payment success. So from the app side, nothing unusual ever happened. Same request, same success, just a beat slower. And that right there is the whole value of the layer. Because if you tried to pull this off yourself without an orchestrator, your app would suddenly be on the hook for 5 separate things. It would have to tell the difference between a generic decline and the specific kind that's actually worth a card number retry. and not go retrying a hard decline it should leave alone. It would have to hang on to enough transaction state, so the amount, the currency, the item potency key, to retry cleanly. It would have to run the detokenization itself, which, and this is the real catch, drags it straight back into PCI scope, the exact thing you adopted tokenization to escape. It would have to decide which retries are even allowed, since not every merchant wants card number fallback. And it would have to log which path each transaction took, so you can actually tell whether tokenization is earning its keep. Now, there are three more jobs that don't really fit on a sequence diagram, but they matter, so let me name them quickly before we move on. First one, lifecycle events. The card networks are constantly sending asynchronous notifications. So a token gets suspended, a card gets reissued, an expiry gets bumped, and these can show up hours, even days after the payment. The orchestrator quietly consumes all of that and keeps its stored payment method records current. So the next transaction either just works or fails fast instead of failing slowly. Second, multi-acquirer routing. The moment the orchestrator sends a transaction to a different acquirer, say a local one in the cardholder's country, that token still has to be valid over there. And whether it is, that comes straight back to how the token was provisioned, which is exactly where we're headed next. And third, network divergence. Visa and Mastercard just don't build their token systems the same way. The cryptograms out of Visa Token Service and Mastercard MDES have different formats. They come from different APIs and they follow different lifecycle rules. So the orchestrator hands you one clean interface and quietly soaks up all that difference underneath. So before any of those flows can even run, there's one decision sitting quietly underneath all of it. And honestly, it's a really easy one to get wrong. Here's the deal. Network tokens get provisioned under something called a Token Requester ID, or TRID for short. Think of it as a registration with the card network that says who asked for the token. And here's the part that matters. Whoever holds that registration is the one who decides whether your tokens are portable. There are three common models here, so let me walk you through them. The first one is a shared TRID under a payment processor. It's the quickest to get going because the processor provisions the tokens for you. But there's a catch. Those tokens are now bound to that processor. So the moment you try to route a transaction somewhere else, the token just doesn't work. The second model is a dedicated TRID, operated for you. Here, a vault or an orchestration provider holds a TRID that belongs to your business. So now the tokens are yours, and they'll work across any acquirer that accepts network tokens. And the third is direct, TRID ownership. This is where you go register with the networks yourself. You get maximum control, sure, but you also take on maximum certification overhead. And that's really tough to justify unless you're operating at serious scale. So here's the punchline. If you're planning to use more than one acquirer, and let's be honest, any merchant chasing authorization rates gets there eventually, then a shared processor TRID takes that option off the table. You get the tokenization benefit on your main processor, and then you lose it the second you try to route around it. So match the TRID model to the routing flexibility you actually want, and make that call before you provision a single token. An orchestration layer is worth a separate tier in your stack because network tokenization is not one feature. It is a set of obligations that recur on every transaction and compound across acquirers. The orchestrator owns the choreography, the per transaction cryptogram state, and the failure recovery policy, and it presents all of it to your application as a single, stable interface. Thanks for watching. The full docs are at docs.hyperswitch.io, and the architecture write-up is linked in the description. If this was useful, like and subscribe for more Hyperswitch deep dives.